Good morning. So we reached today another important section, again, not just for life, not just for the purpose of taking this course, but for life in general. The notion of independent events, which is intimately connected to the notion of conditional probability that we learned in section 8.1 in the previous lesson. So we kind of alluded already to the type of questions we're going to address, right? So I mean, in the previous lesson, we talked about how the one event, if it is realized, can affect the probability of another event, right? When we ask questions like the probability of E given an event F is already realized. So here we ask again this, we ask a slightly different question, but related to that. And let's write it here near the title. So the question is, does the occurrence of one event affect the probability of another event? Okay, so the question is not always that obvious. I alluded to some situations in which the question is pretty obvious, right? So for example, let's say, and I think I mentioned this before, let's say you have an experiment in which you roll a die and toss a coin. Okay, so if I say the event E is rolling a 5 or 6, and event F is tossing a heads, right, when you toss the coin, the probability of the event E obviously is going to be 2 over 6, two outcomes, 5 or 6 out of 6 possible outcomes. And the probability of F, of course, by itself is 1 over 2, right, tossing a heads. But one doesn't affect the other. We don't need too much theory and discussion about it because it's pretty obvious that one doesn't affect the other. If I say what is the probability of E given F, right, assuming that you knew that you'd actually toss the head, so assuming that this event F is actually realized, it doesn't take as much math discussion, so to speak, to realize that the probability of E given F is the same as the probability of E. F does not affect E, and we can get that from the context of the problem. The real issue is when things are not so obvious from the data given, and that's the goal of this section, to pinpoint when these two are when these things are not obvious. So I'm going to anticipate already even the definition here. In these particular examples, E and F are independent. So when the answer to the question I posed in the beginning of this class is no, right? The occurrence of one event does not affect the probability of another event. That's when we say that these events are independent. We're going to have a much more rigorous definition, math definition, pretty soon in this section. But again, I want to point out what is actually intuitively clear in many cases. We need math when it's not intuitively clear, but in this case it is. Sometimes actually even the intuition may play us some tricks. I'll talk about that with the famous examples of casinos games, or luck games, when certain outcome appears repeatedly and then people mistakenly assume that the next instance of the experiment will have a different probability just because of the prior things that happen, So they miss the fact that events are actually independent, but we'll get to that immediately as we move along. Right now I want to show you with two examples side by side when this question is actually not that obvious to answer just by intuition, the occurrence of one event, whether it affects the probability of another or not. So I'm gonna give you two examples, like I said, side by side. The data in the example, the experiment in the example is going to be the same in both cases. So we're going to have a group of students taking math or biology, and these students are either freshman and senior. Freshman or senior. So we have basically a breakdown of this group into 4 categories, right? By the course they take and whether they are freshman or senior. So, and I'm gonna denote the 2 events here in this problem. I'm gonna denote, let's see, by M, a student randomly selected takes math, and by S, a student randomly selected is a senior. And we have 2 versions of the data, version 1 and version 2. And let's illustrate this data with 2 tables like that. So we have a freshman, senior, and then math, bio. So it's a 2 by 2 table. And here we're gonna have 10 freshman students taking math, 10 of them taking biology, 5 seniors taking math, 5 seniors taking biology. And then here a similar table. We have freshman, senior taking either math or biology. And here the numbers are slightly different. Well, not just slightly, just different, right? So freshmen taking math, let's say we have 2 students in this group, 4 freshmen taking biology, 1 senior taking math, and 3 senior taking biology. So let's look at the first version and let's come up with some totals here. So total math student taking is 15. Total bio is 15. Total freshman is 20. And total senior is 10. And so notice that we have basically 30 students in total. Right? Remember, you can add them by column or by row because these are just 2 different criteria of splitting this group of students. Again, it's important to point out here, right? So the sample space is 30 in version 1, 30 students in total. They are distributed either 10, 15, 15 taking math biology or 20, 10 taking being freshman or senior. Okay, so pay attention to the probabilities and the conditional probabilities in particular. So I want to know the probability of a student taking math. Okay, so how many math students in total? We have 15. How many total students? 30. So the probability of a student taking math is 1/2. What is the probability of a student being senior? Well, we have 10 seniors out of 30 students total. So the probability of a senior is 1/3. And now let's pay attention to some conditional probabilities. What if we ask the probability of a student taking math given that that student is a senior? So we know the student is a senior. So now I look just at the row for the senior students and I ask what's the probability of a student taking math. So of the 10 students senior, so now the outcome is reduced to 10. I mean, the total number of outcomes is reduced to 10 because we have, just 10 seniors. Only 5 of them will take math. And so the probability is going to be 1/2. What if I ask the probability that I pick a senior given that the student in question is taking math? So again, pause if you want for a moment. It's important to see how we compute these probabilities, right? This time is a conditional probability. So now given a student that I picked takes math, so now I look at the column of math students, which means the universe is reduced now to 15 students taking math. How many of them actually are senior? Well, only 5 of them are senior, and then 5 over 15 is equal to 1/3. So the thing to notice here is that it doesn't seem that the occurrence of one event affects the other. So the probability of taking math seems to be, it is equal to the probability of taking math and being senior. The probability of being senior is the same as the probability of being senior given that the student takes math. These values don't seem to be affected by assuming one event happened or not. This is 1/2, this is 1/3. So in the language of independence, M and S are independent events. The occurrence of one doesn't affect the other. Now it's very important to point out the reason for this being independent is because of the distribution of these students, the particular numbers, how many math, how many bio, with respect to the total, not because it's not possible for these events to be dependent. Because if I change the numbers, you'll see in the version 2 of the example, as it turns out, the events actually are dependent. So it's important to make the distinction between independence based on the realities or the context of the experiment. So in the sense that, sometimes events cannot possibly be dependent, right? So in the previous example, when I toss a coin and I roll a die at the same time, it is not possible that the rolling of the die outcomes will affect the tossing of the coin outcomes or vice versa. So in that case, independence is pretty clear from the context. But in this example with the students, independence must be verified to see if it appears or not. Must be computed, in other words, via probabilities to see if the two events affect each other in terms of the probability. So let's do the same exercise with version 2. In this particular case, we have 6 students. How many? We have we have 10 students in total, right? So total math students is 3. Total biology students is 7. If I add them by freshman or senior, total freshman population is 6. Total senior population is 4. So we have total students, 10 total students in the group. And then let's ask precisely the same questions. So what is the probability of a student taking math? Well, we have 3 students taking math out of 10 students total. That's 3 over 10. What is the probability of a student being senior? Well, we have how many? 4 seniors in total out of 10 students total. And I'm going to leave it like that without simplification just to keep the denominators the same. So the probability of a senior is 4 over 10. And let's ask now the conditionals. The probability of a student taking math given that the student is a senior. Well, given that the student is a senior means that I'm going to be restricted to 4 seniors total. And of these 4 seniors, notice that only one of them takes math. So the probability of M given S is 1 over 4. The other way around, the probability of S given M. So now I'm looking just at the math column. So out of the 3 students taking math, one of them is a senior. So the probability is 1 over 3. So I hope it's pretty clear that because 3 over 10 is not equal to 1 over 4, the probability of M is not equal to the probability of M given S. And furthermore, because 4 over 10 is not equal to 1 over 3, obviously the probability of S is not the same as the probability of S given M. So the occurrence of one of the two events affects the probability of the other. So in this case, M and S are not independent. And I hope it's clear that the story is the same between the two examples. The only difference is that the data points are different. So in one case, it turns out the probabilities are the same, conditional and not. And in this case, in the second version, they differ, which means they are not independent. So that's important because when you make these estimations, it's extremely important to know whether the occurrence of one event affects the other or not. Again, sometimes from the context is easy, although sometimes errors are made intuitively as well, and I'm going to mention that toward the end of this class. But on the next page, let's formulate more rigorously using mathematical, with a mathematical formula, so to speak. Let's formulate exactly what we mean by two events to be independent. So stay tuned for the second page. Okay, so let's go over the definition, which we kind of already implied in the previous page. So two events, E and F, are independent if the probability of E given F is equal to the probability of E, or equivalently, the probability of F given E is equal to the probability of F. The two are actually interchangeable. If E, I mean, like if E is independent from F, F is independent from E. So I mean, like let's write it like that, right? So E independent from F, from whether it is affected by the occurrence of F, is the same as F independent from E, right? So that's why we don't, it doesn't matter which one comes first, so to speak, right? So a group of events, two or more, are independent if the occurrence of one doesn't affect the probability of the others. So there is a slightly more useful criteria for independence. It's given as a theorem, and I'll illustrate it because that's also a nice opportunity to review some formulas. But I want to emphasize, and I can't actually emphasize this enough. People often don't hear me out when I say this. It's very, very important to understand these formulas in a logical manner. Some of these formulas, if you actually understand what they say, should be as obvious to you as 2 + 2 = 4. So let me state that again. If you understand the notation and what the formula actually states, it should be as obvious to you as 2 + 2 = 4. If it's not as obvious, it means that you're not used yet with the notation. You still don't process in your mind, right, what independence means, and so on and so forth. Because why is that? If one event doesn't affect the other, and then I'm asking, look at the first definition here. If I'm asking, what's the probability of E given F? And let's say that you know that these are independent, right? So the probability of E given F. Well, if F has no bearing on the probability of E, given F shouldn't change anything about E. So it shouldn't be a surprise that the given F, what's the probability of E? It's the same as the probability of E, given nothing, right? So this is the most obvious statement related to independence via formulas. If they are independent, the probability of F given the other doesn't change anything. It's the probability of the same event, F. So please keep that in mind because this is like a self-check to see if you understood the whole concept. Like I said, we have a formula related to independence. Now remember, we learned previously, let's take the first definition here. We learned previously that P of E given F, the formula for the conditional, is P of E and F divided by P of F. And because on the other hand, if independent, so if E and F are independent, On the other hand, P of E given F is also equal to P of E, right? So I mean, if the two are if the conditional is the same as P of E, from the last two, if we multiply by P of F on both sides, we get that P of E and F is equal to P of E times P of F. And just for practice, we could do the same starting with P of F given E. Okay, so if we have P of F given E, if we knew that is equal to P of F, so if we know that these are independents, from the previous formulas, P of F given E is P of E and F, or F and E, remember that's commutative, divided by P of E equals P of F, and again, if we multiply both sides by the probability of E, we get that P of E and F is equal to P of E times P of F. Okay, so pay attention to this formula, right? The formula for the intersection of two independent events, because that leads to, like I said, to one important theorem related to independent events, which states that E and F, two events, are independent if and only if the probability of E and F is equal to the probability of E times the probability of F. So this serves as a criteria for criterion for checking for independence. So if the probability of the intersection is the product of the probability, then the events are independent, and we can extend that to an arbitrary number of events. So if you have some events A1, A2, AN, these are independent if and only if the probability of the intersection of all is the product of the probabilities. And you have in the homework a bunch of quick questions in which you can illustrate this formula. So for example, let's say we have a bunch of probabilities. P of E is 4 over 21. P of F equals 7 over 12. P of E and F is equal to 2 over 9. And the question is, are E and F independent? So it's just a matter of checking this formula, right? So is the probability of E and F the product of P of E times P of F? Well, let's check. 2 over 9, is it equal to 4 over 21 times 7 over 12? Well, we can do some simplifications here. This is 1 over 3. This is 3 on the bottom. No, 2 over 9, as it turns out, is not equal to 1 over 9. So E and F are not independent. All right, so that is the default or the ultimate criteria for independence when the context is not obvious whether these are independent or not. Because like I said, if you go back to the rolling a die and tossing a coin at the same time, the outcomes of the coin doesn't affect the outcomes of the rolling of the die and so on. Here's a quick example similar to this. Let's say the probability of E is equal to 0.25. The probability of F is equal to 0.36. And the probability of the intersection, let's say, is 0.09. Just use the calculator and quickly realize that 0.25 times 0.36 is equal to 0.09. So the probability of the intersection is equal to the product of the probabilities. So therefore E and F are independent in this example. Some other formulas can be combined with this one. Just remember, whenever you have independence, then you do have this additional property of being able to distribute the probability over an intersection. Again, once we know that the events are independent. So we're going to continue with some other examples on the following page. Probably it's going to be the last page, but we'll see. So stay tuned for the next page. All right, so let's continue our practice. Let's say in the third example, let's say we know that E and F are independent. And we are given that the probability of E is 0.2, the probability of F is 0.4. The probability of E and F, let's see, well, okay, so I was going to give the answer actually. So we know these are independent. So then the questions now, okay, so find the probability of E given F, the probability of F given E, the probability of E and F, the probability of E union F. So at this point, why don't you actually take a moment and see if you can find the answer, pause the video and try to do it on your own. And assuming you just did that, let's actually check to see your work. Again, remember, we assume that these are independent. All right, so that means the first two questions should be pretty straightforward. One doesn't affect the other. Probability of E given F is the same as probability of E, which is 0.2. Probability of F given E doesn't matter. It's the same as the probability of F, which is 0.4. The probability of the intersection, well, we know that this is the product of the probability if the events are independent, so you just multiply 0.2 with 0.4, and that gives you 0.08. And then finally, the probability of the union. Now, first of all, we remember one formula from prior sections. This is the probability of E time plus the probability of F minus the probability of the intersection, which, because they are independent, and only because they are independent, that intersection is the product of the probabilities. And then you can plug in 0.2 plus 0.4 minus the product of those two, which is 0.08. I put an extra 0 there, sorry about that. So 0.2 plus 0.4 is 0.6 minus 0.08, which gives you 0.52. So let's move on to some other examples that are slightly trickier when we have to put this together, and examples in which independence is not actually mentioned, but it is implied or derived from the context of the problem. Okay, so you might remember, by the way, these problems when we picked marbles from a box without replacement. So here's to mirror a similar example. Okay, so suppose you have a box that contains 6 red marbles and 4 white marbles. And pay attention to the experiment and compare it to the one we used when we learned conditional probabilities in the previous section. 2 marbles are drawn from the box with replacement. Okay, so you pick a marble, you put it back, mix it all over again, pick another marble. So you should realize that the first marble does not affect the second. Okay, so we have independence, of these events, the independence of the first marble with the second marble. The problem, it doesn't mention that, but because the state is so once you extract a marble, once you put it back, the state of the problem is the same when you extract the second marble. Nothing changes, right? I mean, when you're ready to extract the second marble. So this is an example in which independence is derived from the context. And once you keep that in mind, you should always use, of course, the probabilities related to the independence, like the one when we have P of E and F equals P of E times P and F. So you always multiply the probabilities when you have AND or the intersection, once you're guaranteed to have independence of events. So let's illustrate how that works. Let's say the question is, what is the probability that both marbles are red? Not part A, that's just the question. So both are red. What's the probability of both are red? Well, first of all, we kind of need to realize that we need to split it into two mutually exclusive events, because both are red means that actually let's put part A because I'm going to do a similar one. Both are red, not done this one, the next one I want to split it in that case. So both marbles are red, right? So that means the probability of the first one to be red and the probability of the second one to be red. Both events are independent, so because of the property we mentioned before, that's the probability of the first one being red times the probability of the second being red. So obviously it's going to be 6 over 10, 6 red marbles over 10 times 6 over 10, that's 36 over 100, the probability of both being red. All right, so part B is going to be one which is going to require the split into mutually exclusive events. What is the probability that exactly one is red? So again, think and absorb a little bit of the question to realize that the need for splitting into two mutually exclusive events, because we extract two marbles with replacement. If I want exactly one to be red, there are two possible situations mutually exclusive when that happens. You can either have first red, second not red, or first not red, I should have called it white because that's the only possibility in my case, and second red, right? These are mutually exclusive, or remember it's related to the union of two events. So therefore, by the formula, this is going to be simply the summation of the probability of first red and second not red plus the probability of the first not red and second red. Remember, and is associated with the intersection, and now use independence. This is going to be the probability of first red times the probability of the second not red. I should have called it white, but I'm going to keep it like that till the end. Plus the probability of the first not red times the probability of the second being red. And now we can finally compute these probabilities. The first one being red is obviously 6 over 10. Not red is 4 over 10. First one being not red means 4 over 10. Second not red is 6 over 10. It's always over 10 because it's with replacement, right? So we have 24 plus 24. That is 48 over 100. So that's one example, or that's another example. I want to go over one more, and finish with that example with the casino and explain why people sometimes have this wrong intuition when it comes to independent events. So stay tuned for a short last page. All right, so let's take a look at this example. And I think I mentioned before that really in this chapter, most of your time should be related to reading and thinking rather than computation. This is a very nice problem that on one hand, it shows why these concepts are so useful in life. The first of all, probability theory in general, but also the independence of events and how they come up with in real life applications, and actually important applications if you think about. That's one nice thing about this example. Secondly, solving this example is going to be just basically 2 multiplications. So couldn't be faster or easier. But obviously we have to think it through and see what the problem is asking us to do. That's the most of the hard work in this case, and not the computation. So really force yourself to understand the problem, because that's where the difficulty is, not the computation part. So take a moment to write this down, pause the video to write this down, and then we're gonna walk through the problem and then solve it together. So the title of the problem is quality control, right? So it says that a furniture company hires 2 people who work independently, and there's your keyword, which now should raise a flag already, to identify defects in workmanship. So this company hires 2 inspectors to identify, to do this quality control. If the probability an inspector misses a defective piece is 0.2, what is the probability that both inspectors pass a defective piece? So this is another problem in which we don't have to waste our time with setting up the probability space. Like, for example, what's the experiment, what's the sample space, and so on, okay? So the experiment obviously is going to be picking a furniture at random. The event is what's the probability that furniture is actually missed the control test, basically, right? I mean, the probability that a defective piece missed the control. But that's not important, because it's already laid down. The probability is already given. The question here is, what is the chance that both will miss a defective piece if one of them working independently, again, that's the key word, has a probability of 0.2 to miss the defective piece. So basically, if the inspectors work independently, you can think of each inspector as being represented by an event. For example, inspector 1, let's call it E1, this event, states that inspector 1 misses a defective piece. You don't have to write this down. I just want, because most of you probably will know what the answer is immediately, and it's fine to write it down. But I want to write it in the language of the formulas we established before with independent events. And the second event, inspector 2 misses a defective piece. If they work independently, then these 2 events, E1, E2, are independent. To say that both miss a defective piece, both miss the defective piece, is to ask what is the probability of E1 and E2. But because they are independent, this is equal to the probability of product of the probability of E1 and E2. It's perfectly fine to, once you understand what the problem is asking, to just write 0.2 times 0.2, because I'll know what you're talking about, right? So this will be obviously 0.04. Okay, so that's important in real life, right? Because each of them working independently to check the same thing, to check the defective piece, reduces the probability of missing that defective piece. And the key thing is in the independence of them working together, right? Because, for example, let's say they work together and one says, oh, I checked this piece, it's all good. The other one says, okay, fine, you checked it, okay, let it go through. So then in that case, of course, the probability will still be 0.2. You won't reduce the probability of missing a defective piece. So the key thing is working independently, and that is the reason why you multiply the error probability, if you want, right? I mean the mistake, the chance of making a mistake and missing a defective piece. And then the company can have a plan, like in part B. Let's say they want to have a less than 1%, right? Less than 1 in 100 chance of missing a defective piece. How many should they hire? Well, each additional inspector reduces the probability further. If I hire 3 inspectors, obviously the probability of missing a defective piece is the probability of each of them multiplied, right? 0.2 times 0.2 times 0.2, because again they work independently. This will be 0.008, which satisfies the requirement that it should be less than 0.01. So you need to hire 3 inspectors. So let me finalize with the famous examples of people missing the independence and making huge mistakes at the casino. So, for example, you are at a casino and play, and let's make it actually very simple, right? This is not really a play, I suppose, a game in the casino, but let's say the game is to flip a coin or toss a coin, and heads wins, tails loses. Okay, this game is played repeatedly. You show up at the table, and as it turns out, 10 players before you or 1 player before you played the game 10 times. So the game was played 10 times and it was tails in a row. So before you arrive at the table, it was tails, tails, tails. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here you arrive and you say, I'm gonna bet $1,000 for heads. I mean, because I have so much bigger chance. Because I mean, what are the odds that after the coin landed up 10 times a tail, what are the odds that it's gonna be again a tail? It begs the question, like, you know, it begs the situation, so to speak, that the coin will land heads after landing tails so many times. So of course, because all of these games, so each instance is independent, the probability of heads given 10 tails beforehand, it's still the probability of heads when you flip a coin, which is still 1/2. If you are fine with a 50% chance of losing $1,000, then by all means you play it. If you're not fine because you mistakenly believe that the probability of heads is so much higher this time around, then you shouldn't place such big of a bet. So the probability of a heads is still 1/2 no matter what happens beforehand. What I think it happens in this case, why many people have this wrong intuition, is because they ask in their mind. We are species that have memory, right? So we have memory in our minds, and we can't basically, I mean, it's very hard for us not to actually analyze the big picture. And we make a mistake in the intuition in this case, because in our mind, instead of asking, I show up at the table and a coin is tossed, we ask in our minds incorrectly, for the purpose of this game, 10 coins are tossed. What are the chances that, or 11, 20, if I count myself, right, in addition to the previous 10. So I ask incorrectly in my mind, 11 coins are tossed. What are the chances that 10 of them will be, or 11 of them will be tails? That would be a very, very low probability, right? So if I ask the question, I toss 11 coins and all 11 coins end up tails, then obviously that's a very, very low probability. Is 1/2 times 1/2 times 1/2, 11 times 1 over 2 to the 11 is going to be very low. But of course, this is not the game you play. You don't show up in the beginning at the casino and then you throw 11 coins. All these 10 tails, it's already past history. However unlikely is to have 10 tails in a row. That already happened. Okay, so unlikely events sometimes do happen, right? It's very unlikely to have 10 tails in a row. However, sometimes it happens, and if it did happen, that has zero relevance on what happens with the 11th toss. So what a mistake in the intuition is that people essentially use the wrong space of probability. When you show up to the game, the space of probability is basically one coin with two outcomes, heads and tails. People, because they are prone to actually analyze history, right, derive conclusions from the experience, from the past experience, they incorrectly use the space with 11 coins. Okay, and they look, okay, like there are 10 tails beforehand, such a small chance to have 11 tails, because they view the space of probability, including the prior games. Same thing with the accidents, you know, battery failure, right? If there is no relevant information related to that, there is no reason to fear that the battery fails in an airplane. However, Boeing 787, to go back to the previous example, that's a different question, because that ended up being relevant piece of information, since there was, let's say, a certain defect in that component. So we'll probably have more chances to talk about this stuff in the office hours. Make sure you bring these questions, because they're fun to talk about. And that's it for today.